derivatives of polynomials and exponential functions. So let's talk about, it says the simplest function of all, the constant function, f of x equals c. What's the derivative? Remember, the derivative is tied to the slope. As we can see, it's a horizontal line, which has a slope of 0, because it neither rises nor falls. So the derivative for that function, which is f prime of x, would equal 0. Okay, so the derivative would be also a flat line at 0, because again, it's the slope. In every point, it's 0. All right, but now we go to power functions. Power functions in the form of x to the n. And here is like the simplest power function, x to the first power, right? Straight line. And so any straight line has just a single slope, and the derivative is that same number. So the derivative function would be a function which is 1 at all times. So the derivative here is also a constant. Oops. And so f prime of x would be this function, which is at 1. Okay, so because the slope at every point of this f of x is 1. So that's, now, a few simple cases that the book has talked about. We didn't necessarily talk about them, but where it was found that the derivative of x squared is 2x, the derivative of x cubed is 3x squared. Do we see a pattern here? And a lot of you know the pattern, basically. So x squared becomes 2x, x cubed becomes 3x squared. What about, if you see a pattern, what's going to happen to x to the fourth? Yes, continuing this pattern, whether you know that rule or not, you can see that the exponent of the original function, like in this case the 3, the 2, becomes a coefficient, right? On the derivative function, and then what happens to the power? As we take the derivative, it lowers by 1. So two things happen. The exponent, the original exponent comes in front, becomes a coefficient, and the exponent lowers by 1, yes. And so sure enough, that is what happens. We predicted it. It's true. And here's the rule in general, right? And that's exactly what it's saying. The original n, the exponent, comes in front, becomes a coefficient, and the power drops by 1. So, excuse me? This is 3.1. So these are examples, right? X to the 6, same pattern. Even x to the 1,000. T to the 4th, really just a different variable there. So all those are using that power rule. Now, in general, okay, here's the power rule. And it says it enables us to find the tangent line. Now, the tangent line is the slope of the tangent line is the value of the derivative. And we'll see that. Like in the homework, it'll ask you to find the equation of the tangent line. And it's basically, it's about finding the derivative at that point. But I want to talk about something called normal lines, which is something you might see in a physics class. And the normal line is perpendicular. So again, if the slope has a tangent line, okay, tangent line, that slope also, there's a line called a normal line that's perpendicular to the tangent line. And this has applications in physics. And so in the homework, for example, you will be asked to find both of those lines. And I think we realize, but just to say if the slope of the tangent line, M1, was 2 over 5, who remembers what the slope of the normal line would be, therefore, because it's perpendicular? What would be the perpendicular? Yes, negative 5 over 2. Or do you remember that? Slope of a perpendicular line is the opposite reciprocal of the original line. So that's what we do. All right. New derivatives from old. So we're talking about here about combining functions or making a different function. Now, this is a simple example. If you're simply multiplying the function, the original function, by a constant c, like instead of x squared, you have 5x squared. What happens when you take the derivative? Well, that 5 just sticks around. Okay? It's still there once you take the derivative, and just gets multiplied by the derivative. So that's one rule. And here we have the sum rule. So if you're taking the sum of two functions, we do this a lot. If you want to take the derivative of the sum function, you split it up, and you take the derivative of each part, term by term. Okay? And even if you have more than one, you just take the derivative of each one. And we will see that in the homework. We will see that on the worksheet and on the quiz. And same for the difference, right? You subtract them. Again, you just divide and conquer, take the derivative of each one. Now, the last thing in this little section that I want to mention is talks about exponential functions. Now, we're going to get to those derivatives later in a few weeks, actually, where we're going to look at those in general. But there is a very special function which has a base e. So, and an e is an extremely important number in really all of mathematics. It's probably the most important number ever. And it's a big deal in this class, the number e. And e, here's one definition of e. And e, as you may know, and you can find it in your calculator, it has a value of about 2.18 ... It's an irrational number. And it's a number that's used for the growth of living things, basically. So the function e that has a base of e, so f of x equals e to the x, like I said, is a very special function. I'm going to say it's really the most important function in this class. And now e is between 2 and 3, so e to the x is between 2 to the x in terms of its steepness, and 3 to the x. What's special about this curve is that right here, let's look at this point, as the value of the function is 1, the y-coordinate is 1, the slope is also 1. And then we take another point up here. This value of the function is anything, really. It's e to the x, because here we have x. What they're telling you is that the y-coordinate and the value of the slope, the steepness of the curve, are the same at every point on this curve. The value and the slope are the same. Now, what does that mean? Well, it means that, bless you, if you take the derivative of a function, of this function, remember the derivative is the value of the slope. So the derivative of the e to the x function will look identical to the original function. It won't change if you take the derivative. And that's the only function this happens to. It also means, like, if you have a population that's growing, getting larger, and what this is saying is, as it gets larger, it's going to grow faster because the rate at which it's growing is proportional, directly proportional to the size of the population. The size of the population would be that y-coordinate. The rate at which it's growing would be that slope. So they are directly proportional. Now, sometimes there's environmental limitations to how a population can grow, but if there's no limitations, then that's what happens. Okay, so once again, this is what we're saying. If you take the derivative of e to the x, you still get e to the x. And we're going to see this function all throughout this course. And I think that's all we're talking about today in this first section. So we're going to go to the homework now.